So we are onto the output layer, right? Because we already talked about kind of how to use multiple neurons in one layer. And then we moved on to talking about how to like stack layers on top of each other. And the final thing, I guess for now, to talk about is this output layer. So here, we're going to change the domain to use digits, okay? So this data set is called the MNIST data set, MNIST. And you can just Google that. And the idea is that we can provide in kind of like pictures of handwritten digits, and our neural network should be able to identify that this is the number 5 and this is the number 9, just like our human brain can, okay? So what we're worried about for now is like, I guess, even constructing a neural network, right? Like the hypothesis function that can do this. And maybe even before that, the question is, well, what does it mean to take in an image? And what that means is, imagine that each pixel here, right, is represented by a different number. And we'll see that in just a little bit. But imagine that each picture is represented by a different number, and maybe the darker the pixel, that's represented by a larger number. So maybe these are all represented by the number 100, and then down here it's closer to 0. Okay? This is like grayscale. So there's in an image like this, there's actually 28 pixels by 28, which is length or a total of 784 pixels. And the way that we'll represent that, if you kind of think about how we've passed through our data so far, right? We've had one for like each feature at a time in one vector. So maybe we had 3 for the cell area, and 5 for the cell perimeter, and 4 for the number of cell concavities, and so on and so on and so on. But the point is, it's been one long vector. With an image as well, we're going to have one long vector. We're just kind of like unspool, this image. And we'll talk more about that later. But the point is that we just need 784 digits, each from 0 to 100. So that's what I do here. Okay, and I'll go through this in a second, but I'm just creating a vector of length 784 to represent an image, okay, the pixels of an image. And how does this work? So I'm doing random integer, torch.random integer, and then the first argument is the range, right? So this is going to return values between 0 and 100, all these values. And then I'm specifying the dimensions. So I'm saying I want you to return a vector, or basically one row and 784 columns, which is what you can see is returned. So this is what we're going to want to pass through our neural network. So then the question is, okay, well, what do we want to get back? What can our neural network return to us so that we can make sense of it? Because previously, we had a neural network, it basically had something binary of, is this cancerous or not? And for that, it just returned a single number between 0 and 1, right? And 1, we said, the closer to 1, the more likely the neural network was predicting cancerous. So what do we do when we have kind of like 10 different digits to predict? It's not just 0 or 1 anymore, a binary result. What you do is something like this. All right, so this is a list, and this is a prediction from a neural network. And the way that we interpret this is each element of this list represents a probability of, or the neural network's prediction of how likely the observation is to be each individual digit. So it's saying there's a 5% probability it's a 0, this observation is a 0, and a 62% probability that the observation is a 1, and a 3% probability that's a 2, and so on. Okay? So that's the output. And the next thing to do is basically, say, well, how do we go from x of, 1 by 784 to then get an output of 10 numbers? All right, we need to like construct a neural network that does that. Let me not cheat. Okay, so how do we construct this using what we know about matrix algebra? So we'll do nn.linear, and this is going to take in 784 features So we need a weight for each one of those features. So that means we should have 784 weights. And then the number of neurons we want is kind of up to us. Lots of times you use a number that's 1/2 the number of features, so like 392, but we'll do something significantly smaller. We'll do 64, just because we want a smaller and simpler neural network for now. Okay, so that's our linear layer, right? It takes in an observation that has 784 features, so we need 784 weights. And then the next thing we have is the sigmoid function. So pass these outputs to the sigmoid function, and then here we're going to take, remember, we'll effectively get a different output for each neuron. There's 64 neurons, so we'll pass these 64 neurons to now the next linear layer, right? And now each of the neurons in that layer has to take each of these 64 outputs, right? So we want to basically say that, you know, how long should each vector, how many weights do we need for each of these neurons? Well, 64, okay? And how many neurons do we want? Interesting, right? How many outputs, right? The number of neurons, we're going to get a separate output for each neuron. And how many outputs do we want? We want 10 outputs, right? One for each of the options, right? There's, you know, it could be the number 0, 1 through 10, or 0 through 9. So we have 10 different options, and so we want 10 outputs. So we produce something like this, okay? And let's try this out. So we start with x, right? X is a 1 by 784. Then we pass this through, and let's just see what happens. And it breaks, and it breaks because our type is wrong again. Let's do x dot float. How many times do we have to do that? And there we go. And let's just look at the shape, right? One row, 10 possible outcomes, right? It's, you know, 10 values are returned. So a list of length 10, just like we kind of wanted. You may already have some problems with this. There's a couple issues with what we have here. So here's the issue. One issue is this does not look like a probability. So like, how can you say there's a negative 0.07 chance of something occurring? That's one problem. The other problem we have is we oftentimes want with this output, we want a single number to dominate. So if you have like 10 things returned, and let's say 9 of them are like 0.1 or even like 0.01, well, that only gives you a remaining, if 9 are 0.01, then the remaining 10th can only be 0.91, right? These 9 options are taking up a total of 9% probability, and so we only have 91% left to say, I really think it's this thing. And that's, we want our neural networks to do a little bit better than that. We tend to want, you know, one number to dominate, okay? So that's kind of the goal, is we actually want to exaggerate the value that we are most confident in. And there's a function we use in math that tends to do a pretty good job at exaggerating values that we are confident in. And the way that it does this mathematically is it will increase larger values a lot more than it will increase smaller values. And the function that does that is the exponential. Okay, so we're going to see this by example. All right, so if we do, let's just show a couple examples. Let's say we have a relatively small number, like the number 3, okay? And then I do torch.exponent, and it says it has to be a tensor. So let's make this a tensor. So torch.tensor 3, and this is, I guess, a small number. Pass that through here. We get a number 20. Now that may seem like a big increase, but let's try a relatively larger number, like a large num. We'll make this not that large. Let's say we'll just do the number 8 and replace this. And now apply the exponential to this. See the difference? yes, it increases this number 3, but it drastically, right, a small difference in the value that we pass through results in an extreme difference after applying the exponential function. So that's pretty cool because we want to exaggerate, get an output like this, like maybe this 1.02 as opposed to the 0.847, and really exaggerate it. All right. So if we do this value, we get this 2, you know, maybe not super, and we do this 0.847. So it does exaggerate it, right? It does do it, maybe not as extreme as our example, but you can hopefully start to get the point. Right? That's what we're going for, is we want to really exaggerate our larger numbers, okay? The other thing the exponent does is, you know, these negative numbers actually disappear with the exponent. So let's say here's a negative number. This torch.tensor, and we'll set this equal to negative, and then we'll apply the exponent here to a negative number. You'll see what happens is it gives us back just a number less than 1, but it takes our negative numbers and they are positive now, okay? And the more negative we are, the smaller this value is. So it's keeping the same order of our numbers, right? This is bigger, you know, 1 is bigger than 0.8 is bigger than -1, but you know, it's kind of transforming, and this is bigger than this is bigger than this, but it's exaggerating our large numbers and it's turning our negative numbers into, you know, fractions essentially. Okay, so the first thing we're going to do with these values is apply the exponent. So let's just do this. This will be our y hat predictions, okay? And then we'll do torch.exponent of y hat. And okay, now we get back these different values. There's one more issue here, okay? These are not probabilities. How do we know that are probabilities? Well, with probabilities, we kind of know it from common speak, right? The probability something occurs is between 0 and 1. We have numbers that are greater than 1. The other rule about probabilities is that the sum of all possible outcomes should be equal to exactly 1. Okay? And this is a really important rule. Sum of all possible outcomes should be equal, I say must be equal to 1. All right? So there's an easy way to go from these values to then say, you know, the probability that this occurs. Okay? And the way that you do that, let's call this my absolute, or I don't know what to call it. I'll call it like the raw values. All I have to do is divide by the number, is add up, is divide by the sum of these values, okay? So this becomes more clear if maybe we give an example. Let's say we, you know, let's say that, you know, we say that like 2 out of 5 times, you know, someone roll. I'm trying to think of a good example. So let's say we're rolling a dice, and 2 out of 5 times, and it can only land on 1, 2, or 3, and 2 out of 5 times it lands on the number 1. 1 out of 5 times it lands on the number 2, and 2 out of 5 times it lands on the number 3. So these are kind of, you know, the different outcomes and how often they each occur, 1, 2, and 3. But if we want to turn this into probability, you just divide each of the numbers by the sum here. Okay, so this sum is 5, and then you say 2 divided by 5, 1 divided by 5, and 2 divided by 5. So now there's a 20% or 40% chance we get the number 1, 20% chance we get the number 2, and a 40% chance we get the number 3. And notice that all these values are positive, and we get 40% plus 40% plus 20% gives us 40 plus 40 is 80, plus 20 is 100. So that adds up to our 100%. So what's the point? The point is to turn this into a probability, we can simply take the sum of this, torch.sum of our raw values, and divide by that number, okay? And divide by the sum of those values. Okay, now this whole thing, if you added it up, this should equal 1. See that? This whole thing, because we applied, take the sum and divide by that sum, now we have a set of outcomes that do fall, where the total probability, if we add up the probability of each of these potential outcomes, that equals 1, right? And we have each of these individual probabilities is between 0 and 1. So that's pretty good. Now that procedure that we just applied, where we first, took the exponent, applied the exponent to these values. Think about it, we first applied the exponent, and then we divided by the sum of these values that we applied the exponent to. That's called the softmax. So I'll show that to you mathematically right here. So we took a value x. This is what we got from, this is the prediction that we made. And then we applied the exponent to it. So we did torch.exponent of it. And then we divided by the sum, torch.sum of this numerator. Okay? And that is the softmax. All right, and the goal of applying the softmax is, again, we are kind of both exaggerating this first step of applying the exponent that exaggerates our larger value, our relatively larger value, so it makes them even more large, and makes them really outshine the other values. And we also, by dividing by the sum of the exponentials, we convert this into probabilities. And this is done so much that PyTorch, of course, gives us a function to do this. So that's what this last layer does, is the softmax. Okay, so now I'm redefining my neural network, and then I'm passing through this, and what do I get? I get, valid probabilities. Each one of these is between 0 and 1. This kind of dominates with training our neural network, which we'll do in a little bit. We'll see, that more to be true. And then notice that the sum of all these possibilities should equal 1. So we'll do torch.sum, and we get 1, right? Because something must occur. There's a 100% chance that something must occur. So this is it. This is what a neural network looks like mathematically. And we will move on to the input layer in the next lesson. See you guys there.